Hello, in the last video we looked at problem 12.39 from Numerical Methods for Engineers, 8th edition, which you see here on the right hand side of the screen. Through the last video we set up the four equations that would help us to solve through LU decomposition, what we're going to look at in this video, for the variables A, which is the acceleration in the system, R, which is the tension in this chord, S, the tension in this chord between mass 2 and 3, and T, the tension in chord 4. So if you didn't see the last video, it would it'd be recommended to go back and have a look at it. You'll be able to see how we walk through the free body diagrams and using Newton's second law, come up with a system of equations that look like these here. We did create this coefficient matrix and the response vector here for no other reason other than maybe just to ensure that we didn't have any zeros along the main diagonal, which is something we generally don't want, we can't have. So I'm going to move on ahead into MATLAB now, and let's proceed to solve this. So what I'll do is I'm just going to take a screen grab. I'm not going to worry so much about the matrix here. I'll rely on the equations, so I don't have to flick back and forth between windows. What I'll do is I'll move straight into the MATLAB environment. I'm going to open up a new live script in here, move on to text. Let's give it a title here, and let's look at maybe let's put it into a title. Let's caps lock it, LU decomposition to solve a system of equations modeling a system of blocks on a sliding plane. Right, that title got slightly out of hand. But what I will do is I'll put in numerical methods for engineers. Let's see, problem 12.39. All right. Maybe make that less bold. Back up a wee bit bigger than that there. Look, all right, like that. Okay. So what I'll do is let's put in a section break onto that, and then I'm going to paste in my equations. Just make my space slightly smaller. Let's make that a wee bit smaller, something that I could see. I'm just going to stick in another section break, and let's put a title here. So we'll try in this one, and let's call this one here parameters. This actually would look better if that was a to make this one here a heading 3, a wee bit smaller. Alright, so parameters, let's go back into code. So here I can, if I look at my equations, I have an M1 is an unknown, it's a response, R is a response, G is a parameter, theta is a parameter, and mu is a parameter. Let's go for that. Let's say for just call them M1, suppose the underscores. M1 is equal to a value, M2 is going to be equal to a value, M3 is equal to a value, M4 is equal to a value. So there's the mass values. The values are given to us in the problem. M2 is 10, M3 is 8, and M4 is 5. So let's run this down from 15 down to 10, down to 8, and down to 5. Right, and I'll always, I know it takes up more time in the videos, but it's always good to comment the codes, and it is just something that I always do. Mass of block 1, and there's an kg or something. I'll use kg. master block 2, master block 3, and finally master block 4. Nice. Okay, so there's our masses. Now the next thing what we'll do is let's just stick in mu is equal to mu2 is equal to, so if I can recall correctly, I think the mu1 on block 1, 0.8 and then 0.2. So mu1 is equal to 0.8, and this is the coefficient of friction between the block and the surface. Nice space. And then this one here is 0.2. Control C between block 1, better written, block 2 on the surface of the incline, if you like. There's mu1 and mu2. Now let's get something in for gravity. 9.81. That's is the acceleration. Say due to gravity, acceleration in the common gravitational field is really what it is. Meters per second to the minus, just putting the re-raised to there. Right. What do we need to know? We need to know what theta is, what the angle here is. Theta is equal to, there is going to be pi over 3. So this here is the angle of inclination of the plane to the horizontal. See, there's rods. Okay, that's theta. Right, that's it. There's our parameters done. So let's put in a section break in here. Let's go back into text and let's give this here. I believe this was a hidden 3. I think this one. Hidden 3. Let's just do our calculations here. Right, let's go back into code. So what we'd like to do here now is set up, effectively model these equations up here. We're going to model them though as if they were in the in matrix format, matrix multiplication format, which is the AX is equal to B. So the AX there is going to be our coefficient matrix, and it's going to truly reflect what we have written here. So let's call our coefficient matrix, we'll call that A for now. Let's open it up, and A, I'm going to have M1 in the top row. We have, there is an M1, we're going to go for an R, which is a 1, 1, no S, no T. Okay, I'm going to have an M2, let's just move this over just for the look. M2, I have a -1, a +1, and a 0. So my R is a -1, my S is a +1, my T is a 0. Alright, let's go on to the next one. I'm going to have an M3. Right. I don't have an R, but I have a -S, a -1S and a +1T. So I don't have an R, I have a -1 and a 1. And finally I have an M4 here, you can just see them. I don't have an R, don't have an S, and I have minus 1 over T. Right, so there's my A matrix. Now, for LU decomposition, what we do is we need to decompose this composition, or this coefficient matrix, into its lower and upper components. That'll generally be done by Gaussian elimination. But we do have a function in here called U. And we can see it in here, LU matrix factorization. I think they're both lowers in that, LU. But so I want LU for A. But what we want to do is I want to output that into a lower and an upper. So that there's the function. But let's split that into a lower and an upper. And we'll call it L and U. Right, I'm going to semicolon that out. In fact, what I'll do is I'll unsemicolon that. Let's run this, see how we look. So that is factors us out. Our lower matrix has 1s along the main diagonal. And then what we have here is our scalars, our reduction factors on the lower. And then we do have an upper matrix, like an upper banded matrix by the look of it, which is fine. Right. Now, well, let's write in what our forcing function values are going to be. So that they're going to be my B's. Right? And then what we're in fact going to do is solve for a D, which is a kind of a placeholder sort of a vector, and then ultimately for our AR, S and T. So this is what I'm going to put into my B vectors as an M1G by sine of theta minus mu 1 cos of theta. Right, so let's try that there. I'm going to open up our vector here. So this is going to be M1 multiplied by G multiplied by, let's open up our bracket, and we have sine of theta. Right, that's going to be our first one. Now what do we do after that? Minus U1 cos of theta. Minus 1 times the cos of theta. Close that and close that. That's our first one. Second one is going to be very similar, except it's M2 multiplied by G multiplied by same thing, M sine of theta minus mu 2 by cos theta. Our third one is minus M3G minus M3 multiplied by G. And our fourth one there is minus M4 by G. Minus M4 by G. So I won't semicolon that one either. I'm going to semicolon this one back out. Just want to make sure that looks alright, which it has. It's computed. Okay. So let's semicolon that out. Alright, so we have A decomposed into a lower and upper component, and I have my forcing vector there, B. So in LU decomposition, what we do is we solve for this intermediate column vector. In numerical methods for engineers, it's given as a D. So our D is going to be equal to, actually make that a lowercase d. We take our lower matrix, right, and then what we're going to do is we're going to solve for this D by backward substitution. So in backward substitution, we'll do a backward slash, right, and we'll go for a B. Right. I'm not going to bracket that off, right, or semicolon off, just let's check. And what I'll do is I have an intermediary value here for D. Right. And we'll come back and comment these. And now what I'm going to do is I'm going to solve for my x's. Right. So I'll just call this, let's call it small x. Right. X is going to be equal to, I take my upper matrix now, right, and then what I'll do is I'm going to use this backward slash again, but I'm going to backward slash in the D to that. So let me semicolon that off and let me run this. So what I'm going to turn out here, hopefully, is going to be a column vector of 4 rows, and the rows are identified as A, R, S, and T. So if A is positive, I'm on the right track, providing there, of course, that the equations that I took out of the free body diagrams were correct. But I would like to see A specifically be positive on this. If it is negative, it means there that I incorrectly guessed the direction of travel of the system. And again, I should go back, change direction, and rederive all the equations out of the free body diagram because of the effect of friction. Alright, so let's just see what we have here. In X, I'm at 0.4261, so I'm showing an acceleration of 0.4261. It is positive. Because it's positive there, what I am thinking is that my guess was correct at the time, and everything is right. Okay, so we'll go back here. So I'm just going to drop in a couple of comments. This one here is my coefficient matrix. This here is the decomposition of matrix A into its upper and lower diagonals, echelon form as they call it. B, this is my forcing function vector. Take this one here out, X, just put it up to the top line. Just keep B the same. And B is my, it's like intermediate. I keep thinking of calling it a placeholder. It's not a placeholder as such. It's an intermediate, maybe solution vector, column vector. Right? And then this here, X is going to be, this is my system responses. System responses all to 6, which is A, R, S, and T. Right. So that's some there. Yep, I think everything else that should be looking all right. V1, V2, 15, 10, 8, 5, mu1, mu1 0.8. Let me just double check that. Yep, mu1 was 0.8. mu2 is 0.2. Gravity, yep. Pi is good. ALU, yep. So I'd be happy enough to state that there is the solution to it. So hopefully you get a little bit out of the video, and between this one here and obviously the one before it, which derived the equation which allowed us to use LU decomposition and MATLAB's own function for decomposing the coefficient matrix A into its upper and lower forms to solve for them. Actually look at would be to do Jacobi or Gauss-Seidel on it, but it would be unlikely that it would converge, given that the diagonal is so non-dominant. But non-dominance or dominance, is only a good indication that it definitely 100% will converge. If it's not dominant, doesn't mean it won't converge. The likelihood of it converging is less, though. That's really that. But we'll look at that in a different video, maybe. So thanks very much for tuning in. If you have any questions or anything, please contact me, drop them into the comments in this, or get in touch through any of the other means available. Okay, thank you.